Thanks. So, as you all know, my main topic is helicity, magnetic helicity in my PhD thesis. And in this paper we considered magnetic helicity in a different gauge, which belongs to the advective gauge family. And the reason why we did it because magnetic helicity is known to play a very important role in dynamism. And in an earlier paper we showed that you have to get rid of helicity to lower the quenching. And we also saw in the same work that by redistributing magnetic helicity, you also alleviate this quenching. And so this is the reason why we consider this. And we are particularly interested in our family, in our gauge, which we call a vector resistive gauge. But this one proves to be unstable, so we make a gauge transformation, which I will call lambda method. Then I will talk about the instability and its nature, and later I will also talk about magnetic helicity transport. So now at the beginning of all MHD is the induction equation, and that one you can uncurl. And well, you can uncurl it in a resistive gauge such that the time evolution for A looks like this. It's called resistive because this is the resistive term, this is magnetic resistivity. Or you can also uncurl it in a different gauge, for example, in our gauge, which we call the vector resistive one. And it's called a vector resistive because we have this resistive term here and an advective term here. Of course, you can also just remove this, then you certainly have the advective gauge. So now we have our advector resistive gauge, and we make simulations with that one. So with the time evolution of the A field, we have the other usual MHD equations, right? And then we run our simulations, and pretty much all of them crash. So they are unstable.
What's CL?
Okay, CL is a parameter which we want to change later on. Which we, if it's 1, we have the Lorentz force. If it's 0, we just switch off the Lorentz force. That's basically a switch for the Lorentz force to make kinematic simulations.
What is the numerical instability that happens? Because the magnetic field and the current should not depend on the gauge, right?
In theory, yes, but I will show you why it comes. It's numerical errors.
I don't understand what simulation you are running. I mean, you put this.
Okay, yeah, right. Sorry. It's resistive MHD for an isothermal compressible gas, and we have a box with a cubic box with periodic boundary conditions. Yeah. Okay, so now.
What do you mean with crashes? What happens? So
we have an extreme buildup of kinetic energy, and also.
So it's a crash in the velocity.
Yeah.
UMS.
Yes, and also BRMS at the end.
Yeah.
Also Lorentz force.
Initial is the velocity.
So now we apply a workaround. We work in the resistive gauge, and we apply a gauge transformation with this number, which transforms from the resistive to the advector resistive gauge. And we also make evolve this number. So we have an additional equation for number. And this proves to be, well, this is of course stable because A does not directly depend, it does not depend on number. So basically, simulations are run in a resistive gauge, which is stable.
Then it doesn't work in tensor code, or even if you do work in tensor code, I'm aware of this. The resistive gauge is the default gauge, unless you're running with scalar marker 1, in which case you're running in a modified convective resistive gauge.
The resistive gauge is the Coulomb gauge?
Resistive gauge is not the Coulomb gauge. Resistive gauge is the one which has that unpulled form of the induction equation, which is chosen so that there is a Laplacian only for each component.
Yeah, but doesn't it reduce to the, in the limit eta 0, doesn't it reduce to the Coulomb gauge?
In limit eta equals 0, it reduces to a lot of gauges.
If you start with a Coulomb gauge and then in this case, would you remove the Coulomb gauge?
Don't think it's guaranteed actually, but it might be. I'm not sure.
What does the Coulomb gauge look like?
The Coulomb gauge means something to give the divergence of A0.
But you don't want to use Coulomb gauge because in that case you have to impose divergence equal to 0 at every step.
Yes. So
That will involve solving a Poisson-like problem, which will involve a lot of computation. So as far as you can, don't solve for Coulomb gauge is our idea.
So this is a plot for the time and the normalized magnetic helicity, or the RMS value of it. And the red curve is the direct gauge, the vector resistive gauge, which becomes unstable at this point, which is even before the nonlinear regime. And while the random method keeps to be stable. Okay. Now, why is it unstable? So if you look at the evolution equation for A in that vector resistive gauge, there is this term here, this diffusion term. If you expand it, you will see that it actually contains terms like this. And this should be 0, right? But numerically it's not necessarily 0. Especially if you look at high K's, where you get some numerical errors. And that comes in your B, because that changes your B, which also changes your J, and which changes your Lorentz force, and you've got an increased velocity, and the code crashes.
Something to keep in mind here is that KAR in the second panel is sort of the estimated value of B you get for A if A were purely were completely non-differential. And so we see here that very huge rotational component in A. So the effect of the KAR is so much above the BAR means there's a huge rotational component in A, which is causing numerical problems.
And in these plots you also see that, especially in the high K, you've got these increases. So now what we did next is we wanted to look at how is helicity distributed in the system. And we did this in the kinematic regime. That means we switched off the Lorentz force. This is something you can do in pencil code. But just modify the factor I showed you before. So just set a 0 and there's no Lorentz force. And in that regime, for high Reynolds numbers, it behaves more or less like it behaves like a passive scalar. And here I plotted time and again the normalized root mean square of the helicity. And for the two gauges, a vector resistive gauge and a resistive gauge. And basically after a very short time they reach a plateau. And this plateau I used to create these two diagrams. So basically I just took the average over time, this value, and took the Reynolds number, I just created these plots. So in these plots you see Reynolds number and the normalized magnetic helicity. So this is for the resistive gauge, and this is for the vector resistive gauge. And in the resistive gauge you see a very nice power law, like R m to the minus 1/4, which is pretty much independent of the Reynolds numbers. So we've got Reynolds number 1, 5, and 10. Sorry, Prandtl numbers. And while for the vector resistive gauge, you see some kind of hook here, which we initially didn't really expect. So we've got some power law here, which is different for the different Prandtl numbers, and then this hook here. And one explanation for this hook is that since you keep the Prandtl number constant, also your Reynolds number increases. So the fluid becomes less thick. And so you will have more efficient transport of helicity to smaller scales, because you will create small eddies. So and basically this one we fitted with this formula. So now we also compared the helicity with a passive scalar. And we did it just by introducing another equation. Just put in a scalar which had an initial constant gradient and just let it evolve. And here I've plotted the power laws of the two helicities and passive scalar. And in the kinematic regime, the passive scalar looks more or less like the H in the vector resistive gauge, but for the saturated regime they differ quite a lot. So this dotted line is passive scalar and dashed line is helicity and resistive gauge.
What's the saturated regime?
Saturated is when the magnetic field strength reaches equipartition.
I mean, is with law as well as without?
Oh, wait, first, good.
So if you look at that formula for F, you notice that basically there's an inflection point, and then there's resistance points. And that right there, that one line is the entire reason that this project got started, also like a year ago. Because in that period, all the velocity components, well, all the velocity-based transport is a vector. And we're comparing it to a passive scalar because a passive scalar just gets permanently diffused. So this provides us a method to see how things change from this permanent diffusion. Departure from certain.
So how do I know that the gauge works?
What do you mean by gauge work?
Okay, I know that the resistive gauge doesn't work because it basically explodes simulation.
It's like that.
Yes, but how do I know that the other works?
Gives the same result as a resistive gauge for B and B.
But then it doesn't explode. So how do I
So it doesn't explode. In the second method, it doesn't explode.
With the number method, it's stable.
The vector resistive gauge, when calculated directly, causes a crash, not in A, but in the velocity field. When we do it with the lambda method, there's no crash in the velocity field, and A isn't also
but
not
so the lambda method belongs to the general class of error effect in C, right? So basically, you're writing an equation which is numerically exact, but there is an error which analytically should be zero, but numerically it's not. So you add another equation which takes care of that error and affects it out of the box.
No.
It doesn't affect it.
You don't even solve that equation, but you solve another equation so that you can get the results of this equation by the transformation.
Well, you see, you use the MHD equations only in the resistive gauge. So usually you only use this one.
Directly, the effective gauge is not solved anymore. the point is we are interested in the quantity A dot B, and that depends on the gauge. Now, in the vector resistive gauge, if I calculate directly, I cannot calculate it because it will explode. So what I do is I calculate it in another gauge and then do a gauge transformation to find what that magnetic density will be in the vector resistive gauge.
Yeah, but your gauge transformation has a lambda, right?
The gauge transformation has a lambda.
Which is also evolved according to that.
Exactly,
equation.
yes.
So what I'm saying is that that evolution
Yes.
basically serves you to back out to essentially kill your error. So you are allowing your code to develop an error,
There's no
and there is another equation that follows the error, and you
No,
subtract
no,
it
I
from your
didn't
code.
say that.
This is not getting affected out of the system.
No, no. So you have an equation for the you have an equation which has an error.
No.
That is the your error is the kernel graph,
We have
right?
a term which
Yes, exactly.
there was
You're
a
right.
huge irrotation component.
No, but there is an error, which is a
That's
grad
fine.
of cut.
That's fine. But you see, if you think your way, then the AAR is the one that should go into the equation for velocity. Right? See, what goes into the equation for velocity is J and B.
Yes.
B is calculated by being called a field. Now, if your way is correct, then you will solve for AR, do a correction to find AR, take a curl of that to find B and J. Right? That we are not doing. We are doing AR, taking a curl of that to find B and taking a curl of that to find J. So the actual evolution equation doesn't even know that there is something else happening.
But what does the gamma n stand?
Well, it's
Lambda just
only
doesn't
enters-
yes, it doesn't enter anything
only
else.
enters when
It
it
just gives you the AAR.
So it's after the simulation.
No,
No,
so
during
the
the
simulation.
next step.
During the simulation, but didn't really affect
It-
the
it-
simulation.
Exactly, yeah.
Is it,
Aside from the
is it very hard
It's
to
like
turn on the
diagnostic.
lights?
It's a side.
Sorry?
It's a side.
On the light.
Turn down the lights.
Diagnostics.
It's
So go back into the
Lambda
simulation.
never enters
Yeah,
any
turn
dynamics.
it even further.
Wait, so your simulation does not explode.
Yes, somebody does not play.
So why is there a simulation crash?
If
No, but-
we run AAR directly,
Solving this
In
equation.
this gauge, in the direct gauge, it crashes, but in this one, not. And in this gauge, you see, there is no back reaction of lambda to A. So the simulation was pretty much independent of lambda.
Then by some accident lambda did blow up. When the simulation will stop, you will get infinity for AAR or garbage.
So the lambda is kind of a diagnostic. It's really
Yes.
well, if you treat this as a diagnostic, basically, the only time you ever use lambda is when you're calculating some property of AAR. B is not a property of AAR, so we never use lambda for anything that we use.
And I'm the one fully. Then goes light.
It's cool.
That's an actual light.
So you
Yeah, you need some
solve
time
directly
to-
the resistive gauge.
You need some time to warm up.
And then you do a transformation from that resistive gauge using that lambda.
So we only do that when we absolutely need to. In fact, we actually need to do that. Otherwise,
But that has no effect on the dynamics.
Yes.
I have a question why you actually want to have a
Yes. Because
different gauge?
And because it's stable.
That's the good
Go
question.
back-
That's what
Go back to
Simon will
like
show us.
the slide you had discussed.
That's what he will now show us. Why is this gauge important?
I mean,
Why do we care?
So right here,
Yeah, well,
you see that flux time.
it's half. Yeah.
so you see that age is actually a vector. I mean, we've got a vector term in there for the density. And so we're interested in the direction of density. And it's quite spot.
This you don't have in the resistive.
There is that term, there's also another term. I don't know if you have that in your slides.
No, actually I had it once, but I took it out actually. It's not.
The other term is a dot u gauge. And if you have any clear idea of what conceptually a dot u b is, more power to you, I know.
So it's more that you can investigate gather the elasticity fluxes.
Exactly. There are some other perks. That is amazing.
Okay, so yeah, exactly. Now what you can see here is that for the saturated regime, the velocity and the vector resistive gauge has actually a higher power for high K as the resistive gauge, and we believe that it's because when you create small scale eddies, the velocity gets cascades more efficiently to smaller scales because we're working with a vector resistive gauge. Right, actually, here I've got a slide which is basically some work which Alex and Axel have done some time ago, and it was introduced in a paper like 2 days before submission. So, then we want to talk about it.
So should I go back? So going back a slide would be. Okay. So I don't want to go back a slide. Yes. Okay, so that work was done in the resistive gauge. And it involved a system. So here's Z. Here was a midplane. And the helicity, there was this forced helical turbulence. And the helicity and the forcing, and let's put an actual boundary here. All these distances are supposed to be about the same. The helicity and the forcing was a nice cosine, let's see, and then 0 in the wings. And the goal there was to look at the helicity trend, and this right here was low, eta, high, eta, approximately constant eta turbulent. So the total turbulence is approximately uniform for the flux. There were regions of high resistivity, which will destroy helicity through this term. And there's a region of low eta with a dynamo going on. And you can think of it as sort of as a disk, but disks normally have opposite sign helicities across the equator. But yeah, so somewhat inspired by disks. And we have vertical field connections here. So the idea, so what we were looking at that flux, and this is in the resistive gauge, as I said, the default gauge of the pencil code, which, by the way, in your paper as you're writing it right now, your uncurled induction equation is written up wrong, because it's assuming it's written up for the wild gauge. You may or may not care. So I assume it's wrong. You're probably not running the wild gauge. And we were looking at the flux of helicity. And we're actually doing it as a even more restricted regime here, and looking at the flux out of this subdomain. And the best fit we could find was diffusive. It's a turbulent diffusion, but very strangely, the turbulent diffusion coefficient we found was significantly below what you'd expect just from the strength of the turbulence. But still, I mean, it's the best fit we had. We ran with it. If we look at this plot here, so we can ignore this curve for now because we weren't running in that gauge. The Pascal scalar has this nice peak at the driving scale because, well, there's a uniform imposed gradient and then there's turbulence at the driving scale. And the resistive gauge also follows pretty much the same cascade here, which means that the resistive gauge is showing clear signs of turbulent diffusion. It's showing the same cascade as Pascal scalar, and Pascal scalar showing a diffusive cascade, turbulently diffusive cascade. However, it is slightly strange in this plot, which is not this system, that there is even a peak at the driving scale, because the system is sort of statistically homogeneous. And there's no source for spatial fluctuations in helicity. So the fact that there is a peak there can be looked at as some sense indications of some non-diffusive behavior, which may explain why we're seeing different coefficients in treatment diffusivity. But at the same time, there's this very nice, clear indication that what we're seeing is really diffusion. So with that, we are willing to go back. Actually, we would have been willing to go back if we thought it at the time, but now we are extra willing to look at this data. This is the divergence of the flux of small-scale helicity, and this is the resistive destruction term of small-scale helicity, and try to estimate where these two terms will cross, and therefore where the flux term will start to dominate over the resistive destruction term. And that turns out to be about 3 times 10 to the 4, which is nicely well beyond anything that we can actually simulate right now. But it's sort of a prediction that the flux term, diffusive flux terms, will dominate over resistive terms, starting at about a few times 10 to the 4 for the magnetic terms.
Sorry, are you sure about the linear behavior?
Oh no, of course not. Please, please. It's a pretty good fit, but
That's wide extrapolation over a decade. So
closing in on 2 decades.
2 decades.
Yeah, my question was like, why the actual linear behavior is just on the right and not?
Because here we are going in. I think here we're going into
that makes some sense
low RM
because
regimes.
Low RM can have non-asymptotic behavior, whereas high RM you are expecting asymptotic behavior. And asymptotic behavior should be some kind of a power law, which should show up as a linear behavior.
Yeah, but anyway, linear behavior will fit also on the left. So it's like
Not well
Not
actually.
really. It's down here.
No, if you extrapolate that, but if you make yeah, but if you use
Yeah.
also the other.
Exactly. So
I mean,
when
it's
you
like that you put this linear behavior on the right because you want it on.
We are, but
on the
we're
left,
also
but
doing
on
it.
the data.
Note that here, like
when
this
you
guy
want-
here
if
is
you
a
want to
lower,
fit a linear
fairly
behavior
low
on the
RM.
first few lines and extrapolate that, that would not be a good idea because you're looking for
Do
an
not-
asymptotic at
No,
high
I'm
RM.
not saying this. I'm just saying that here, if you do this,
Yes.
This one here is pretty good. But down
Yes,
here,
but not there.
No, yeah, okay,
but-
okay.
But don't take the last 3, take all of them.
yeah, but
No,
it's saying
that's
that
the
it
point.
doesn't,
You
doesn't
should
make
take
sense.
the last
You
one
should- we
because
should
you're
include
looking for
these.
asymptotics at high RM. So
Yeah,
you
but
should
the
give
last
more
one, why
importance
you
to
extra, yeah, but I mean, you take 3 points and you extrapolate the power law, you can
Yes.
fit everything, right? So you need, I mean, those 3 points extend over far less than an order of magnitude.
yeah.
Sure.
So extrapolating power law out of the quantity that don't extend even an order of magnitude
No, no,
in
but-
both directions,
no,
it's a very dangerous.
No, but
We
no, you
can't
extend in both
we
directions.
can't go lower
But
because
the
lower you don't
lesson
expect
from
it to behave
here
like
is
that.
Not quantitative. Lesson from here is not that you have an exponent or something. The lesson from here is just about estimating where we could see differences.
Yeah, but that could have been be invented to the
If you use the first one, if
Yes.
you use the first
These,
one,
these points
it
are
will
not
actually get
expected to follow
shorter.
the same. These two should are not expected to follow the same behaviors here.
Take the first 3.
No, take all 5 of them. Don't take the first 3. Take all 5 of them. Right?
Yes.
Then we look like something like this,
Something like
Yes.
that. Yes.
which will be a little different.
Maybe different by another factor of 50. But that's the order of estimation.
But the other thing is, I mean, these 2 points right here are not necessarily expected for any particular reason to be
In
on
any
the
case,
same
above
curve.
10 to the
so.
5, you can go in the simulation, so it doesn't matter really.
Yeah. Well, 10 to the 3, there's hope, especially if like, well, not right now, but in the nebulous
Let me-
future,
let me-
especially if like we
Let
can
me
get the
put it in
GPUs.
context. If you say that I need to go to this energy to see experimental results of string theory, then what is the amount of energy you are trying to look at compared to what you are doing now? And now you look at this and ask, I need to go to high RM to see this, and then this you can imagine happening, but you can't imagine the other thing. That this just to put things in that context.
Three times. I mean, if GPUs really work out,
Still.
then 3 times 10 to the 4 in a decade or two, quite possible.
Let's try to do that
You are optimistic, sir.
Okay.
But this is
Well, I'll let.
the fluxes are all the total fluxes.
This right here is flux of
So
small
you say
scale
the
history.
components are
For the flux then is the total.
That's the flux. That's the divergence
of the,
Yeah.
of the flux of small scale helicity.
It has to be equal to those.
So it doesn't matter what kind of flux.
That's the divergence of the flux of small scale helicity.
divergence of total flux. Yes.
Yeah,
No,
but
no,
it
no,
doesn't matter if it's
It's the total
it's
divergence of flux or the divergence of the total flux?
It's the divergence of the flux of small scale helicity.
And then summed over the whole surface.
Over the whole surface of your
Yes.
simulation.
Summed over the xy plane.
And the other is integrated over the whole.
Yes.
And the other stuff is
Integrated
integrated
over
over
the whole.
But is it the average of the average integrated, or is the integrated or is the average of the E dot?
It's the average. The E dot B is the average of E dot average of B,
Okay.
but as a horizontal average.
But
Then
that-
average over the box.
But that's
So
different than the average over the whole.
E average horizontally dot B average horizontally sum average over box.
Okay.
What is the form that these flux have? Or is what kind of
We
flux?
believe it's diffusive.
Only
Appears to be
diffusive.
No, no, no.
Yeah, but that was the point.
We think it can be modeled by diffusive fluxes with coefficients which will look like turbulent diffusivity.
Yeah.
But the flux itself is not only diffusive, it has all kinds of terms.
And there's messy diffuse
But is
molecular resistivity terms.
Can
This
you-
is more scale.
Very small scale, yes. Do we have that equation in the paper or here somewhere?
For
this one.
for the small scales explicitly, I don't think he has it in his talk.
Maybe you can write it down.
Is it in the paper?
What do you mean by a small scale?
Small.
Flux of small scale.
So here you are thinking about mean field modeling.
Okay, so you
So you have small scale magnetic field, large scale magnetic field, small. So it is a flux of the small scale density.
But that's misleading. The
Small
helicity is
scale
not
is
small.
small.
the average, right?
The helicity is not small scale. It's the helicity of the small scale fields. But
Helicity is
the
small
server
scale
is
field.
large scale.
Yes.
So it is a misleading language.
What's the scale separation?
The scale separation in these ones,
I can't remember for that.
3 or 5.
3 or 5. There might have been an 8 at most.
Mostly 3 or 5.
In our work, it was again
Because
3 or
that's what
5.
we do. Because that's what we do, mostly 3 or 5. It used to be 3, then we found out that sorry, it is 5.
Used to be 5, then you find out that you could get away with 3.
Yes. Then we
And every once in a while, you go up to something like 8. But if you're running 64, then 8's pretty much the limit. And if you're running more than 64, it gets expensive. Zero total is flux.
Does it make sense to think about
Yes, it does. But
Sort of.
I think
You can always keep the helicity flux along your magnetic field 0 by a gauge force. You cannot. Your gauge force only affects the helicity flux along the magnetic field. Basically, there's a flux term. If we have dA dt is equal to U cross B minus theta J plus grad phi. Maybe there should be a minus here. Then the flux term is equal to blah 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 of helicity plus phi b. Maybe again, maybe there's a minus sign there. Which basically says if you're willing to be adequately pathological, you can set your flux along your magnetic field to be whatever you want it to be. And you can do really strange things with that if you want. If you're willing to go to delta function phi's, as you can imagine, you can do completely messed up stuff. But numerically, we can't do delta function phi, so we're good. Numerically, we assume everything is to infinity.
These simulations have shear, no?
That, no shear. None of the simulations had talked about shear.
So it's only helical forcing.
Only the helical forcing. The other simulations were all uniform. This right here is normal.
They have direct simulation.
All direct.
So this would not be the case.
So anyone, any questions for the stuff that he was presenting on? Any more questions?
Shear is present or
How do I know that the need of a B is positive?
what the question is.
How do I know that that term is
this one.
anticipation of elicity and of creation?
It comes out, you can look at the sign. That right there is E dot
That
B.
depends on the alpha.
No. Actually, what happens is basically dH dt is equal to U cross B, which is EMF cross B. This guy right here is 0. It's only when you decompose into fluctuating and mean components that you split it into a plus or minus, but also it's plus and minus EMF dot B. 2. This guy right here is for the equation for the mean. This guy's in the equation for the fluctuating.
No, but how do I know that that is negative?
What do you mean by negative?
I mean, how do
It's
I
minus
know
sign?
that? How do I know that the E dot P there is anticipation of that?
It's not a dissipation term, it's a production term.
Is it production?
Or it's a transport term. It can be thought of as a term which takes helicity from large scales and gives it to small scales, and small scales gives it to large scales. It separates out the helicity different signs.
Okay.
So it's if you will, it spreads helicity, separates it. It's a segregation term, that's what I mean. Okay.
So maybe I just skip to the conclusions. Well, basically that's what I said. Or maybe the outlook. This is one of the outlooks I could come up with. I see where you saw the hook in this diagram for RM and magneticity, and it would be interesting to understand it better. And for that one, we need higher resolution simulations for higher variance numbers, because we're actually close to 1,000. Or close, means of an order of magnitude from 1,000.
Sorry, I'm not really close to
Class, well,
So 64 cubes where it gets in the
You can't do it.
60-ish.
I mean, no computer can do
The
it.
hundreds, the mid hundreds, you can get by 256 cubes.
Actually,
And
I should say that there are different estimated Reynolds numbers in the literature. So you may sometimes see people saying they're actually simulating a flow with 10,000 Reynolds number. But that's a different kind of Reynolds number. So you can define the Reynolds number depending on the large scale of the flow, or actually how the small scale behaves. So what we are defining is a measure which is much stricter on the simulations. In a different way of defining it, you have to multiply by a factor of 30. Depends on what people quote. It may look like other people are doing simulations with much higher Reynolds number. But this, which is sometimes in fluid dynamics literature called Taylor-Microwave scale Reynolds number, in that going to 1,000 is at present impossible for anyone. No computers can do it.
1,000? No, you can do 1,000. It'd be expensive and not.
I'm sorry, I mean 10,000.
actually we are quite close to 1,000. One of the simulations at 256 cube, but that's only because the prime number is quite high. So that means that the Reynolds number is relatively low. So by adjusting prime number, we can actually go to higher.
If we
Yeah,
manage
this is
for some
magnetic.
reason
Yeah,
get
this is
our
magnetic.
one just go to high Reynolds number on one of the teraflop machines, I don't know what we actually could get to. Maybe we could get to something really bizarre, but
So the highest one that has been done till now is 4096 cube. And that's purely fluid, that's not even magnetic. But that hasn't gone to 10 to the 4, I mean 10 to the 4 I guess.
But that was Pickle, wasn't it?
Sorry?
I thought it was Pickle.
And I'm talking about in fluids.
What's the Reynolds number for that?
I forgot it, but the system size was 4096 cube. And no one else has been able to do that. Other people in big computation typically do 1024 cube. So 4096 cube was done, I think now it's 3 or more years old. It was done when this Japanese computer Arc Simulator was the biggest computer in the world. After that, no one has beaten them.
The biggest civil computer.
Yes. We don't know about non-civil computers.
This is the 500 list.
Yes.
So why, I have a very stupid question. Why in that resistive gauge versus REM, why does that have a slope of REM minus 1 therefore?
Actually, I don't really know why, but it fits quite well.
Well,
It fits so
well,
well, it
there's
looks like
there's a couple
there
things
must
that
be
are
some
going.
theory for that.
We don't really have much point of theory for that, unfortunately. One of the things that should be remembered is eta k squared does not tend to 0 as eta tends to 0. This is the resistive energy dissipation, and it does not actually go to 0 as the resistivity goes to 0. This is a big difference between ideal MHD and non-ideal MHD. On the other hand, eta j dot b does tend to 0. But if you will, there's a difference in the, so this guy right here is seeing this, but exactly how he's seeing this, I'm not 100% certain. The other thing to think about is this is the RMS one, so it's picking up all the contributions from each scale and summing them all together.
And what does that, the last slide in the conclusion slide, what does that fourth point mean? I mean, why is it important that the AR gauge magnetic helicity behaves like a passive scalar? Why is that?
Well, it's important in
Diffuse,
in the sense that it's diffused also to larger scales.
But even better,
Smaller scales.
if we go back to here,
Yeah.
we're not even it's not even picking up, there's, again, remember, the system is sort of homogeneous. We're not even picking up a signal at the driving scale. We're not even picking up a signal at the driving scale. So it's completely, there is a signal at the driving scale, which you wouldn't necessarily expect, because there's no real physical reason for it to be one. The vector gate is completely eliminated that signal.
Any other questions?
Should all calculations be now done in the adjective resistive gauge?
It adds an extra equation. If you
For
are
example, the
interested in
dynamo
if you're interested in helicity,
No, but the
maybe.
calculations have been done always in the resistive.
No. What I'm saying that should the helicity be calculated by this method?
Okay, the reason is the cause is running an extra
No,
running an extra
there is
equation.
no correct gauge.
There is the correct gauge, but maybe
There
you
is
get
no.
some good transport, helicity transport properties which
If
that
you're
that
particularly,
makes
if
it
you
more
are,
realistic than
I would say if you are particularly interested in magnetic helicity.
This
But
gauge
there are a
should be
couple
kept
other
in
reasons
mind.
you might think about it. Then keep this in mind. It adds an extra equation, but then one more extra equation is called that expensive. It's not a particularly complicated equation. If you're running shear, be aware that you are running a partial advection equation.
so this velocity is
The pencil
actually
code
the
does shear through this advection equation. So it does, the shear module basically says phi is equal to u shear.
yeah.
And that is already being used, and that's being done because it makes, because if we go back to here, in this equation, I mean, again, you actually restrict this to S, the shear velocity, but the shear velocity only shows up having a derivative being taken on it. So if you're doing a shearing sheet system, you actually don't know where you are on that sheet. Otherwise, you have all sorts of boundary conditions, non-shearing periodic mess, which just completely kills it. But in the shear, in the pencil code, is that shear is being handled in this fashion.
No, so in presence of shear, so what does this gauge mean? The U is the total US plus
The pencil code default is U is equal to U shear, which is handled in a very different fashion than U. These two are handled completely differently, and this one goes into a US.A gauge, which is basically a shearing effective gauge.
I think your question
this is not what you are talking
It does
about.
not cause instability.
Which is not causing, this one does not cause instability. In fact, it makes everything possible. But it's also worth noting that these two equations are actually handled very differently. So these two velocity points are handled completely separately.
So plugging that in here, this U would be actually our U.
If for the full advective gauge, we do U.A. For partial advection gauges, we do that partial U.A. It's one thing about it.
Alex, in one paper, I think you investigate like the boundary or influence of different gauge to boundary conditions. Do you know if
I don't particularly know.
no? Was there something?
There was the paper which I was talking about there, which was there we did look a little bit at how the boundary conditions affected things. Because that's the difference between having a halo, high A and a halo, and putting a vertical field condition here. That wasn't a gauge investigation. We haven't done any gauge investigation on boundary conditions. Other than sort of
But you're saying
possible.
that there is a different shear at grid 2 gauge. So I don't know. That is what I was asking, but it's not clear.
Was there seen any when you compare like in the till the second gauge crashes? Was the simulation exactly the same, or was
Yeah. Until the crash, it's pretty much the same.
Yeah, this same and then they just like
When they overlap.
No, I mean, oh yeah, that's the same.
So this was what this just told us that our method, I mean this lambda method, actually works, and also the numerics is correctly implemented. And it really gives the vector resistant gauge, I mean the helicity and the vector resistant gauge.
And I mean, like for the other things of the simulation also.
I mean
magnetic field and
velocities.
velocities and.
Well, I'm not sure if we had
I mean, does the gauge, the vector resistive gauge, have different to the resistive
well,
gauge?
only up to the crash.
We never checked. I don't think we ever did. We took the velocity field from one and subtracted from the other. I don't think we ever did that. But the energies and the velocities match.
Okay, that's okay.
Well, actually, you can see already slightly before the crash, because now these pulse spectra are taken at a time just before the crash. So here you see the two different helicities, the dashed line and the solid line, and this is a cut just some time before the crash. And there, actually, the velocity already is different,
Okay.
Very high.
and also the magnetic field.
But you start also with different velocities
And
in the beginning. Or the,
No, this is state to
okay.
state.
This is state, okay.
so even before the crash, the physical values are also different.
They have separated some. They may know they've only separated at high K. So there's a discrepancy there. It's starting at high K and moving to the left. Again, one thing that is worth remembering. It appears that AAR is stabilization, but it's only in the velocity that the instability comes up. So it's not that the gauge is unstable; it's that the whole set of equations is unstable. I think this.
Any other questions?
Then let's